Hello, our team is Jam, and our topic is unsupervised CT denoising with deep image prior. Our research was proceeded with the help of the Medisys AI Lab, our advisor Professor Jongdok Baek, and our TA Songjun Kim. We will explain the previous research, our research and improvements, the results, and the conclusion to our research. These are our team members. Our team name Jam consists of the first letters of each our team members. I'm the presenter Jae Hong An, and the other two members are Aida and Bono. Now I'll explain the previous research. When taking CT images, it is crucial to reduce the radiation dose to prevent secondary diseases such as cancer. However, taking an LDCT or low dose CT image increases the image's noise, thus decreasing its resolution. Therefore, we need a method to reduce the noise of LDCT images while maintaining the minute anatomical features that are required for diagnosis. One of the most renowned methods for denoising is to utilize convolutional neural networks or CNN. CNN generally shows good performance for denoising, but it requires large numbers of input LDCT and target NDCT or normal dose CT dataset pairs in the training process. These datasets are difficult to obtain in real practice because not only do we expose the patient to excessive radiation by taking the same CT image twice, but the movement of the patient also creates distortions in the photos that affects its performance. Therefore, demand for unsupervised learning-based methods without using large dataset pairs has arisen in the medical imaging field. As a solution, a recent study indicates a method called deep image prior, based on unsupervised learning, that is capable of reducing noise with just a single cropped image. DIP first inputs into CNN simple distributions such as the Gaussian noise, and sets the corrupted image as its target. Then, by only using the single corrupted image, the CNN is trained via an extreme number of iterations. While the Gaussian noise resists fitting to noise in earlier iterations, its resistance is lost as training proceeds, and overfitting to the corrupted image occurs. Next, I'll explain our research and the improvements. Our research aims to apply DIP to CT denoising. The schematics of our research follows the image. We first input a Gaussian noise to a network and set the LDCT as the target. After training the network via extreme iterations, we will assess the performance of the output to the reference NDCT. While DIP is known to show exceptional performance in natural images, CT images are far from natural, so we will have to observe whether the denoising performance on CT images is sufficient. The reason we are applying DIP to CT images is because medical imaging requires a stable method for denoising, as it is directly related to the individual's health. Supervised methods generally show a good performance, but it is uncertain whether the network will make a correct inference to the unseen test data. However, DIP denoises the image using the image itself, reducing the risk of wrong inferences. The original paper uses the UNet architecture trained by the L2 or MSC mean square error loss. We experimented with 200K iterations of DIP while following these settings. Moreover, as DIP is expected to show insufficient performance from its difference from natural images, we added two more methods in hopes that it would aid denoising. The first technique is the total variation loss. Total variation loss, or TV loss, is a noise removal filter. It is the sum of the absolute differences between neighboring pixels in the horizontal and vertical directions, and encourages spatial smoothness in the generated image. We use the TV loss because it can complement the lack of information LDCT has compared to the NDCT without requiring additional reference. TV loss tends to smooth out the noise in the image while preserving the edges, which is an excellent property in medical imaging. The second technique is to change the UNet network architecture to an RCON structure. The Residual Channel Attention Network, or RCON, consists of several residual groups, and each residual group consists of several residual channel attachment blocks that include the channel attention block. It utilizes long skip connections and short skip connections for effective training. This model was originally a model used for super resolution, so we removed the last upsampling layer and used the structure for denoising. We use the Archon structure because it utilizes the channel attention mechanism. The channel attention mechanism focuses on more meaningful, informative features. For CT denoising, information in the noised image has abundant low frequency, which is the noise, and valuable high frequency, which is the detail, components. We believe that the channel attention will focus on these high frequency components and aid the denoising performance. Now I'll explain our results. We experimented with 3 doses of LDCT images, 1/2, 1/4, and 1/8, to evaluate the performance of our technique for various LDCTs. For the rest of our presentation, we will only show 1/8 dose LDCT images because it shows the most dramatic effect, but all experiments and observations were held with all 3 doses. First, we came up with a supervised control group for our experiment. The result in the middle, compared to the LDCT image on the left, seems to have been denoised very well. However, if you look closely at the images, some of the features are missing. The minute features disappear rather than being preserved. Next, we have observed the changes in the CT images using DIP with the original setting. Images before 60K iterations are not recovered yet, and the images after 80K seem to overfit to the corrupt image. If you compare 60K iter to 80K iter, DIP seems to show at least some denoising performance, but since the noise is not effectively removed, we concluded that this is insufficient performance. To understand the reason, we have observed the loss graph of our DIP experiment. The loss graph does reveal resistance to noise as indicated by the original paper. However, this occurs at fairly early iterations, meaning that overfitting may occur before all features are recovered, resulting in performance degradation. Therefore, we will need other methods to aid the performance of denoising. We added the TV term with the weight as a regularizor for our L2 loss. The bigger the weight, the greater the smoothing effect. To determine the digit of weight, we observed the changes that occurred in the images from 0.1 to 0.001. The weight should be able to denoise an image, but not so much to blur out its features. From comparing the images, we can see that the most appropriate unit is 0.01. To find the most optimal weight, we incremented the weight by the digit of weight and compared the MSE and SSIM, or structural similarity index differences, to the NDCT. The lowest MSE and the highest SSIM for 1/8 dose is 0.07, and 1/4 is 0.04, and 1/2 is 0.03. By observing the images for different iterations, we noticed that, like the original iteration observation, iterations before 60K are not recovered yet. We also noticed that the image is much more blurred in the 10K iterations compared to the L2 iterations. When comparing the 200K iteration with the 60K or 80K iterations, we can notice that denoising has occurred noticeably. After changing the network architecture to Archon, we observed the changes to the images with the L2 loss. Here, iterations before 40K are not recovered yet, and overfitting occurs after 80K. We can observe more intensely colored regions, which would be the effect of the channel attention mechanism, but it also shows insufficient denoising performance, so we added the TV term. We used the previously optimized TV weights for the according doses, and as expected, adding the TV term noticeably reduces the noise. However, the images seem to be more noisier than the original method, so we compared the performance of each method. By comparing the MSE and the SSIM values, we observed that increasing TV increases the performance compared to their MSE variants. The supervised result shows the best performance, and unlike our expectation, Archon structures showed worse performance than the unit structure. So finally, our conclusion. Unlike our initial prediction, unit showed a better performance than the Archon structure. We hypothesized that this performance gap originates from the adjusting stage of our experiment, where we adjusted the learning times of the two networks rather than the number of parameters. However, we overlooked that the attention calculation takes a long time, so it is not suitable for DIP. Even if good performance can be obtained by increasing the number of blocks in Archon, the training time will increase exponentially in DIP as we repeat the training for extreme iterations. Therefore, it will be more efficient to use a lighter network such as UNet and DIP, which also shows good performance. Moreover, although the supervised method shows the best performance, this is due to the provided test data. And our method shows promising results in denoising with increased MSE and SSIM values from the original corrupt image. Thank you.